Okay, so hi everyone. Again, I'm Jakub. I'm from University of Toronto. Today I would like to talk to you about our recent couple of projects under supervision of Dvira Segal, where we addressed open quantum systems with non-commuting coupling operators in an analytic way. To give you some background, we are interested in open quantum systems coupled to multiple environments, and we propose a non-perturbative method to obtain effective Hamiltonians for those systems. What we try to advertise is that our method can handle both strong coupling regime together with non-commuting coupling operators. I will explain why it's an advancement in a moment. And what we want to do with those effective Hamiltonians is to study dynamics and steady state of open systems. And to give you some more concrete examples of what type of systems we are interested in, I would mention atoms in a cavity, where the environments can be related to the cavity being lossy or losses of atoms. We could also think about nanowire-based qubits, where the superconducting substrate can be based on some metal, or there can be impurities in the superconductor which can cause different types of dissipation or dephasing. The last example are molecular junctions that are studied for heat and charge transport that can also be strongly coupled and included in some bigger environment. Okay. So I will start with introducing the model, and then I will show you the exact procedure that we treat this model with, and I will end up with showing you example discoveries and just studies that we made using this method. To look at the general model first, we consider a general system Hamiltonian. We don't make any assumptions about it for now, coupled to multiple buffs. So I will index a buff by index I, and this buff consists of an ensemble of bosonic modes, which I index with K. So then we have a number operator, a frequency omega, then we have a coupling with some general system coupling operator S, some coupling strength T for the ith buff and the kth mode, and then we have a bosonic displacement operator. The prime example that I will use in this presentation, we can think about a spin impurity coupled to two bosonic buffs. So the system operators will be described using Pauli operators, and we also have to specify some characteristic strength interaction lambda and characteristic frequency of the buff omega. I will make those quantities more precise in a moment. So before I go into my particular project, I want to describe the principles of the method. We call it the effective Hamiltonian method, and it consists of basically 3 steps. So in A, we start with a system that is strongly coupled to a buff, characterized by the strength lambda and frequency omega. What we do first is we extract... sorry. Okay, we have some interference, sorry. We extract one... We extract 1 degree of freedom from the buff in a very specific way, such that only this 1 degree of freedom, called the reaction coordinate, is the only degree of freedom that is strongly coupled to the system, and now the rest of this system plus reaction coordinate is now weakly coupled to the new so-called residual buff. Then we do another transformation called the Polaron transformation, where we introduce back the interactions between the system and the buff. Why? Because for the last step, you want to integrate out the reaction coordinate degree of freedom and end up with an effective system now weakly interacting to the residual buff. And so what happens in the end of this procedure is that we end up with an effective system Hamiltonian that has all the strong interaction with the buff imprinted on it, usually by some dressing functions that multiply the system operators. So this was the original idea. It was making out of assumptions. One of the things was that the coupling operators had to commute, but in many real-life examples, that's not the case. And also here on this schematic, we see 1 buff, but this procedure can be done for each buff separately. Being a little bit more specific, the reaction coordinate is just a type of a Bogolyubov transformation on the bosonic modes that separates the variables as I showed in the picture. And then the Polaron transform is a shift of the reaction coordinate degree of freedom by a value that is proportional to the coupling operator. You can think about it as we choose a basis that is favorable in the strong coupling, which is basically the basis is the eigenvectors of the coupling operator. So one of the advancements done in our recent work is to to generalize this Polaron transformation to the non-commuting case. So basically we have this sum over all the displacement inside of the Polaron transformation. Then at last we project onto the ground state of each of the reaction coordinate modes. Just to mention, the biggest advancement of this method development part was to actually handle how to perform steps C and D, which turned out to be analytically difficult in the non-commuting case. Okay, going to the final form of the effective Hamiltonian, what we end up with is a new effective Hamiltonian which has system operators H and S dressed with some superscript effective, which basically means that it's multiplied by some function of the coupling strength, which I will show in examples later. And then we have a new term in the Hamiltonian that is proportional to the coupling operator, so it's buff-induced interactions. That's how we can interpret that. And then we have a new residual buff that looks the same as the original buff, except now the coupling is weak and the coupling operator is also modified. So again, this is the prime example, and now we will jump to analysis that we are able to make using this method. So the prime example is, again, we have a two-level system with some energy splitting delta coupled to two buffs. One of the buffs causes dephasing and one causes dissipation. So we obtain the effective operators in this model, and the nice thing is that they are the same operators just multiplied by some real functions of the coupling strengths. And what we managed to understand by obtaining those functions is that in the strong coupling regime, the effects of the two buffs are mutually suppressing each other. So for example, on this plot, we see time evolution of the magnetization of this two-level system for a fixed dissipation rate and increasing dephasing rate. So each color is bigger dephasing rate. So what we see is that the dissipation rate is suppressed by the dephasing. This was observed before only using numerical methods, and now we, in this work, we managed to explain this effect analytically and just showcase it for any coupling strength. Another example, more toward condensed matter, is so-called buff engineering of condensed matter phases. So what we did here is we take a look at a non-interacting spin chain, and we coupled it. So each pair of spins is coupled to a bosonic buff interchangeably via different Pauli operators. And what we managed to show is that, again, in strong coupling limit, this model becomes equivalent to a Kitaev XY chain. So here we present that this method can show us how can we discover new phases of matter and new interactions that are induced by bosonic buffs, which can be, for example, implemented using some trapped ion devices. As the last example, I will turn a little bit toward thermodynamics. So here we considered, again, a two-level system, this time coupled to two bosonic buffs, this time with different temperatures. And also the operators had some parameters. So instead of having dissipation and dephasing for each buff, we had some combinations. So we had some rotated Pauli matrices. And we asked a question, what are the optimal coupling operators for heat transport? And what we discovered using both numerical and this analytical method is that in the weak coupling limit, the optimal transport is through dissipative coupling, where the operators commute. And what we discovered is that in the strong coupling limit, the best heat transport channel is through non-commuting operators. So for operators which commutator has the biggest norm, we found that this is optimal for heat transport in this case. Okay. So to summarize, we developed a non-perturbative treatment for strong coupling systems with non-commuting coupling operators. Our effective mapping gave closed-form operators that allow sort of an easy, intuitive analytical study of those systems. And then for the results, we discovered sort of a frustration between strongly coupled buffs with non-commuting operators, and we studied buff-mediated interactions and heat transport in spin systems. So for the outlook, we aim to develop similar techniques for fermionic and spin buffs, especially motivated by impurities in superconducting materials in nanowire qubits. We also want to apply the system to more sort of advanced quantum thermodynamic machines like engines. and then we want to further study buff engineering of quantum phases. And one of the current works that is in progress is to consider buffs in resonance. So we want to consider truncating in our effective method to more than just the ground state, and because of that we could consider systems where the buff is in resonance with the system. That's all. Thank you for listening.
Thank you for the talk. So if I understand right, the effective Hamiltonian is getting by only the ground state of the reaction coordinate?
Yes, so in this scheme that I showed here, for simplicity, we consider only the ground state.
So my question is, how do you know if you're not losing information on only the ground state? Because the reaction coordinate get populated to higher.
So great question. I might have not mentioned or not highlighted enough that here we have to assume that the buff frequency is the largest energy scale in the problem. Then, I don't have a proof, but show case by case we check that that gives us an accurate description of the dynamics and the steady state properties.
I see.
Yeah. So we currently work on trying to expand this method to resonance without the loss of information that you mentioned, and that basically boils down to truncating onto a bigger subspace than just the ground state.
Yeah. So you have like a regime which you cannot account in this case because you don't.
Yes, exactly. So basically we lose processes that involve the excited states of the RC.
But yeah,
yes. So maybe I just comment that why we stay in this regime is because when we just truncate on the ground state, the effective system Hamiltonian has the same dimension as the original Hamiltonian. So the expressions are very easy to interpret. So then there is a trade-off between how easy it is to interpret and how far into toward the resonance we can go.
Yeah. Thank you.
So what does this expansion for now? What expansion is also see large parameters?
So the non-perturbative part is just because I don't expand the Hamiltonian in orders of omega. In some sense we could argue that taking more levels of the RC would be kind of an expansion, but I'm just stating that I don't expand. What I do is I look at the effective Hamiltonian that is not the procedure doesn't involve cutting some terms.